of course, I remember before now, introduce you to multivariate analysis. We did introduction yesterday, and today we're going to continue from this. So in the outline, I'm going to walk you through data matrix today and the covariance matrix. And of course, tomorrow, our focus will be on correlation matrix and miscellaneous topics. So just want us to pay attention to that. So I want to go into data matrix. Of course, when you talk about data matrix, we normally resolve into this. When you have your data set, you may have your data set in a spreadsheet, whether in a spreadsheet or you have it in Excel, you have it, in any spreadsheet. Of course, you collect the data in rows and columns, and the fact that rows and columns are involved, we can actually use matrix to depict this data set. So when I talk about data matrix, this is exactly what I mean. The data matrix, usually is usually rectangular in the sense that the numbers of rows and columns may not be the same. And of course, it contains original observations, as you can see. And when you want to talk about dimension, okay, we prefer using n by p, where n is going to represent the number of subjects or items, or the number of observations, and p will be the numbers of variables. So this is the way we like presenting our data. We want a situation where the objects, the subjects, they're going to occupy the rows. It shouldn't be the other way around. Okay, the object will occupy the rows and the variables will occupy the columns. Now, the data matrix, like I said, contain the original measurements. Your raw or data. Okay, why it is called data matrix? Because it is presented in a matrix form. Now, we can have collection of column vectors from a given data matrix. The column vectors is just going to be 1 by p. You're only focusing on the variables. And we're also going to have the row vectors. The row vectors is actually talking about the observations. That's why you see x1 to xn. Okay? So it could be individuals, it could be items, it could be schools, it could be countries, and so on like that. And it's going to go from 1 to n. Okay? Now, if I have either the column vectors or the row vectors, there are some descriptive statistics that we may want to talk about. The descriptive statistics we may talk about, maybe we want to look into the average, but we have to understand which average are we looking for. If you take a look at this now, if I'm looking for column means, okay, if I'm looking for column means, then it means I'm interested in the mean of each variable. But don't forget, each variable is actually collected across observations, across individuals. So which means if I want to figure out the average here, my n here is going to be the number of observations. Okay? So you can see here, I actually, if you take a look at this, say x bar j. Okay? The x bar j, when I say x bar j, my j actually going to start from 1 until I get to p. So I can, x bar 1 will be the mean of the first variable. X bar 2 the mean of the second variable. Then I'm going to do all of that until I get to the last variable. So that's exactly what I mean. So whether I want to find the mean of the first variable or the mean of the second variable, or alter the other variable, or what I'm just going to do is I'm going to use the same formula. Okay? The formula doesn't change. Okay? Okay, so we can also talk about the row means. But why, there could be some reason why we may need the row mean. Maybe we're actually looking for average for a particular individual. Don't forget what you have in the row. They are the individuals, right? So, and when you're finding the mean for that person, you're taking into consideration the data for that person across variables. In that situation, the number that you're going to have will point to the numbers of variables when you want to add this guy. You can see that? You divide it by P, because this time around, the focus is on the average for a particular individual. Okay? And that particular individual, you have to take into consideration the value that you measured on each variable. You add them all. Okay? That's why you say divide by P, and of course in matrix form. Some of you may be wondering, this is in scalar form. This is in matrix form. Okay? So the first one is in scalar, the second one is in matrix form. Now I want to walk you through an example now. Okay? And let me tell you this, we're actually going to be using software R. It's not as if we can use any other software, but we're choosing R for simplicity. You can become an R expert in 1 week, but you may not be a Python expert in 1 week. And that's why we're choosing R. I want to walk us through the implementation in R. Okay, and of course we have data set in R. Take a look at this. We have data set in R. Okay, that we call empty cows. Has anybody heard about empty cows? If you want to have access to that data in R, if you just write data into empty cows, okay, you'll be able to have access to that. Now, when you take a look at the data frame, data.frame is just, it's going to give you all the data. But you know what I have here? This is not all the data. This is just the first 6 in the data, the first 6. That's why you see head. When I put head into that, it's going to show the first 6. When I put tail, it's going to show the last 6. Does that make sense? Okay, so when I say the first 6, what do I mean? So take a look at this. Let's count that. How many? 1, 2, 3, 4, 5, 6. We have more than that in this data. But because this one, we just, for visualization, for effective visualization, we just wanted to say the first 6. But when you take into this data set, when you look into this data set, the dimension, if you want to know the dimension, then when you click DIM is into the name of the data. Okay, you actually, now it's telling us here that, don't forget the other time I said we have N by P, right? N here is 32, P is 11. That's what it means. So the number of observations here is going to be N, and the numbers of features, the numbers of variables that we have, actually going to be P. Okay, so we have 32 observations by 11 variables, and each observation Okay, we collect data on 11 across 11 variables. Okay, on each observation, and that was done only one time for each individual at one occasion. Okay, now when you have this data set, this is the data set, like I said. But let me tell you this. The way this data set look like now, this is not a matrix. But how do I generate a matrix, a data matrix for this data set in R? Okay, then what you need to do, look at this. Can you see that? X, okay, less than minus AS dot matrix into whatever the name of your data is. And that will automatically generate the data matrix for you. Any question about that? Is there any question? You're good? You understand that? Okay, so what I just walk you through now, okay, the moment you have your data imported into R, you can create a data matrix. And this is how we do that. Okay, that's how we do that. Now, you know, we could have something that may be of interest that we want to figure out. We want to get a basic statistical summary from the data. How do we get the row means, and how do we get the column means? Okay, so there are several ways you can do this in R. We got easy ways, we got hard ways. I'm actually going to show you all of that so that. But whether easy way or hard way, I think I will advise you to use a code you are comfortable with. Use a code that you are comfortable with. I want to show you 3 ways of how to get a row means in R when you have your data matrix. Let me tell you this. When you do not have a data matrix, okay, it may take forever to do this. You know, some of you will be wondering why matrix in the first place. Let me tell you this. Without matrix, that doesn't mean we cannot still get it. We cannot still have it done. But we're going to waste time. You know, with the idea of matrix, okay, we will be able to complete that on time. Like, we're going to save a lot of time. Okay. Now, I want to show you one of the ways to get the row mean. Take a look at this. If you look at the code here, row means, you got to make sure your M in the means is an uppercase. If it is a lowercase, arrow is, you know, is very, very sensitive, case sensitive. Okay, that's going to be a red flag. Now, I've already defined my data X. You know, that's a data matrix X. If you remember here, we define that, right? So when we define that, what do I want to do now? Okay, if you take a look at this, okay, I'm only interested in just 3 observations. Don't forget when I talk about row means, our focus is not on the variables. We talk about row means because variables occupy column position, variables do not occupy the row position. That's why our focus is not going to be on variable when you want to figure out the row means. But our focus will be on the observations. The observations here is probably talking about the type of cows that we have. Now, the moment I actually write 1 to 3, 1 to 3 means I'm only interested, okay, in number 1 to 3. I just wanted to say something. Look at this. In the entire data set, That is number one. Number one in the entire data set is Mazda. Number one observation is Mazda RS4. Number two observation is Mazda RS4 WAG. Number three observation is Datsun 9710. So maybe in this research, I'm interested in the first three observations. If I'm interested in the first three observations, and that's why I indicated 1 to 3. That's why I indicated 1 to 3. If I'm interested in more than that, okay, then I'm actually going to extend that. Now, Arrow has automatically computed the mean for each of these. And this very mean, don't forget, we arrive at this mean by taking into consideration the numbers of variables. Okay. Now, if another way to do this is this, you can just specifically specify the mean of the observation you're interested in. You can see I mentioned the first one, mean of data X. I'm focusing on observation number 1, observation number 2, and observation number 3. That's another way to do that. And this way will give us the same result that we have as the other one. Another one that we want to talk about, another one that we can actually, another way to do that is this, which is similar to the first one. That's how you're actually going to get the row means. So if I want to get the column means, getting the column means the focus is going to be on variables, because we got variables occupying the column position. You get what I mean? The variables occupying the column position. So which means I may be interested in figuring out the mean of each variable translate to the mean of each column. Does that make sense? Okay, so, and what we have in the column, if you go back to the data, take a look at that. These are the variables. NPG, CLY, and so on like that. These are the variables. We may be interested in figuring out the mean of all the variables in the column. We may be interested, in some selected ones, depending on what our research or objective is. Okay? Now, to do, here, I'm indicating that we're interested in the first three columns, and this is how to get a mean for the first three variables. Is there any question here? Okay, so if there's no question, we also have, when you're talking about measures of location, or measures of central, that we also call measure of central tendency. When you talk about descriptive, statistics, in descriptive statistics, we have what we call graphical. We got graphical summary of data, okay, and we got numerical, okay, we got numerical summary, okay, we got numerical summary, okay, of data, okay. Now, under the numerical summary of data, okay, the measures, one of the measures is what we call measures of location. We call that measures of location, or you say measure of, or we say measure of central tendency. Okay, measures of central tendency, and when I'm talking about this, I'm talking about mean, median, and mode. Okay, but let me tell you this. We don't just do what we do. We got a reason why we do what we do. Before I can decide on finding the mean, we got an assumption that probably the distribution of the data is symmetric. Okay, it is it's normal situation where there's a violation of that. Where the distribution is not symmetric, we can't use the mean, and we have to use alternative measure of central tendency, which could be median or the mode. So when you take a look at what I'm projecting now, okay, if mean is not appropriate, maybe because of the probability or distribution of the data, okay, then we're going to make use of median. Okay, and how do we figure out median? So whether mean or median or mode, they are all classified under measure of location or measure of central tendency, and they fall under numerical summary of data in descriptive statistics. Don't forget, we're not doing anything differential here. We're describing, we want to have a numerical, summary of our data. Now, how do we do that of the median? Okay, so if I want to get the same way that we get a column means, we can also get a column medians. Take a look at that. I want to get a column medians for each variable. Okay, this is getting the column medians for the first three variables. So that is the coding now. Okay, and I also and after that, okay, let me tell you this: in the measure of location, we normally use either the mean or the median mostly. We use mean when the probability distribution of the data, how do I use normal? Of course, when you go by your lower level statistics, when you actually conduct a graphical summary of data, there are several ways you can know whether the distribution is normal. I don't know if you have heard about histogram, right? Okay, so we can look at the histogram, we can look at the density plots, okay, and not only that, you can look into the box plots, okay? You can look into the box plot to see if you are working with a symmetric or asymmetric, because the nature of the probability distribution of the data will determine the statistical measure, will determine whether you should use the mean or the median. So using the mean, we are actually assuming the distribution is normal. If there's a violation of that assumption, we're actually going to talk about median. Another measure, another descriptive statistics measure is what we call range. Okay, range. But let me say this: we that also fall under numerical summary, but it has a name generally. We have what we call measures of variation, or we say measures of dispersion. That's another measure within descriptive statistics. Okay, I know you've heard about range. That's what we call standard deviation. Okay, standard deviation. Okay, so you have a range, you have a standard deviation. They're also going to tell you we have also what we call interquartile range. Okay, now when you take a look at this measure, okay, this measure actually, we talk about the spread. Okay, the spread, how your data spread. Okay, to tell you whether the data spread out or is shrinking. Okay, so what range is talking about, range as a measures of variation is actually the difference between the highest and the lowest. Okay, if I want to have a measures of variation and I use range, okay, when the range is very high, we believe that the degree of disparity is actually high. So, but before you can use either range or standard deviation as a measures of dispersion of variation, the distribution of your data has to be normal. If it is not normal, if it is asymmetric, if it is skewed, of course, we're going to make use of it at quarter range. Okay, but how do we get a range here? You know, from how we get a range, okay, this is how we get that. Okay, if I want to get a range, that's how I got that. Okay, we can get a column range. We can also get a row range, depending on what our intention is. Now, that's all about data matrix. Okay, you know, the very first thing that you need in analysis is your data. And the moment you have your data, if it is multivariate analysis, you need a data matrix. From the data matrix, any other thing that you want to figure out can be easily achieved. Okay, now I want to move away from data matrix. Now I want to move into what we call the covariance matrix. Now let me tell you this. What is our intention? You know, talking about covariance in the first place. You know, the covariance actually measures how our variables, how they varies together. It's a measure of joint variability in data. Automatically, the covariance matrix that I'm actually going to have is not going to consist of raw data. Okay? Which means the data in the covariance matrix need to be computed. We actually going to, and what are we going to use if I want to compute covariance matrix? I'm actually going to use my data matrix to do that. But let's see how the covariance matrix look like. Let's take a look at what I have right now. That's a covariance matrix. Let me tell you this. Data matrix used to be rectangular, but covariance matrix must be a square matrix. I'm going to say that again. A covariance matrix can never be a rectangular matrix. A covariance matrix must have the same row and the same number of columns, and that is why you see here, you know, you can see here, okay, and you can also see here. So it's going to be P by P. It's a square matrix. Now, of course, the covariance matrix will tell us the covariation in data, how the data varies together, how they varies jointly. And let me tell you this, in the covariance matrix, the diagonal of the covariance matrix, they are the variances. That will be the variance of each variable. When I'm talking about the covariance matrix, I'm actually focusing on variables. I'm not focusing on observations. I'm going to say that again. When I'm talking about covariance matrix, I'm not focusing on observation, but I'm focusing on variables. Because when you take a look at the first one here, is the variance of the first variable in your data, which means there's a variation within a particular variable. Because when I have a variable, I'm not going to have the same values all through within a variable. There are going to be different values within a variable. So I'm going to have a measure of that. And that's what we call the variance. That's variation within. Variance actually means variation within a particular variable. But when I go off diagonal, then I'm going to be talking about covariance. I'm actually going to be talking about covariance between any two variables, which we call covariation, which measures how two variables, how they varies together, how they varies jointly. Okay? And you know what? If I want to get each of these by scalar approach, I'm actually going to go with that. But you know what? Let me just show you. If I have a data matrix that I already obtained from my spreadsheet, I've already converted that into matrix form. And how do I actually put in place a covariance matrix? Please, I need you to pay attention. How do I get a covariance matrix from data matrix? I want to get a covariance matrix from data matrix. What am I going to do? What I'm actually going to do, okay, I will need to first get the mean of each variable. Okay, I get the mean of each all variables. You know what I'm going to be doing after that? I'm actually going to be subtracting. Take a look at what I'm doing here. I just wanted to take a look at this. Let's take a look at this guy. What am I doing? I'm subtracting the mean of that column from each observation in that column. That's what I'm doing. If you take a look at what I have, x bar 1 or 2, that is the mean of the first column. I'm now subtracting that from each and every observation in that same column. That's what they call centering. Okay? Now, I'm going to do the same here. All the way to the last variable. When I do that, that's going to give me SC. That SC is what we call centered matrix. Centered matrix, that is not covariance matrix, but that is, what needs to be done first for us to be able to get the covariance matrix. Now, after putting this in place, please pay attention. After having this, the next thing I'm actually going to do, I'm going to find the transpose of this guy. I'm going to find the transpose of this guy. The transpose of that guy is actually going to be the sign. That sign means the transpose. Okay? The transpose is changing the row to column or changing the column to row. When I find the transpose of this matrix, I'm still going to have the same dimension. It's still going to give me the same dimension. It's still going to give me a square matrix. Then after that, you know what I'm going to do? Then I will multiply the transpose of that centered matrix with a centered matrix. And after doing that, whatever I got, I'm going to divide. I'm going to use n to divide each element in the results. And that will give me the covariance matrix. So if I want to get a covariance matrix now, I need to first have my data matrix. And after having my data matrix, I need to get a centered matrix. And after getting centered matrix, I need to find the transpose of the centered matrix. And I'm actually going to use the transpose of the centered matrix to multiply the centered matrix. Then what I'm going to do, then I'm going to divide each of the elements in the matrix by n. And n in this case is going to be the number of rows you have in your data. And when you do that, that will give you a covariance matrix. Now, that will save you a time, that will save you so many time of just, computing it one at a time here, using this approach, one at a time here. It's actually going to take forever. That's why we're actually using the matrix approach. Okay, now moving now. I want to focus more on the variances. Okay, why am I focusing not on the variances? I'm talking about the elements in the diagonal of the covariance matrix. We have to emphasize more on that because the variance must have some property. Non-negativity. It's either it is 0 or greater than 0. So we want to talk about that here. Variances are non-negative. Okay? When you find variance and you get it negative, then you are wrong. You have to revisit what you've done. But you know what? Covariance can be negative. Covariance can be negative, it can be positive, it can be zero. That's okay. But variances cannot. And that is why, if you take a look at what I'm trying to say here, you know what I mean? It means the variance associated, the variance of any variable has to be greater or equal to zero for every j, for every any variable at all. That's what I mean. Okay, it has to be greater or equal to zero. And we also have some situation where we have to impose more restriction on the variance. Okay, the restriction is that we don't want it to be zero. It's not going to be zero. Variance must exist. Okay, so I said the sj squared greater than zero as long as there does not exist an alpha, such that we're actually going to have this, such that the sj is actually going to be alpha one hand. The one hand is projection. When you talk about projection of ones in n dimension, 1 1 1 1 1, that's what I mean. Okay, that's exactly what I mean. And you know what? If I have a covariance matrix, okay, we should look like this. Okay, what is the trace? We're talking about mathematical formula trace now. Okay, we expect the traces should be the addition of the variances. The trace of a covariance matrix is adding all the variances together. That's what we mean by trace. The trace of a matrix is adding elements in the diagonal of a matrix, adding all the elements occupying the diagonal. So the trace. Now, when we add all the elements, here we're adding the variances. Okay, adding the variances. Okay, it must be either 0 or greater than 0. That's what we mean. Okay, that's exactly what we mean. By the time we start principal component analysis, okay, in the principal component analysis, we actually gonna have, what we call eigenvalues. Okay, when I say eigenvalues of covariance matrix, the eigenvalues of covariance matrix actually talking about the variances, the variance of each principal component. So that is exactly what I mean here. You take a look at that. We use a lambda 1, lambda 2, up to lambda p. Each lambda represents the eigenvalue of a principal component analysis. So we're still going to talk about that. So they are more or less like variance. Okay. Now, we want to have some condition now. If n is less than p, what is the meaning of that? When the numbers of rows is less than the numbers of p, the numbers of columns, which means situation where the number of observations is less than the numbers of features. Of course, we normally have this in big data. We normally have this in that would be a problem of high dimensional data, where the number of features is more than the number of observations. So situation or where that occur, okay, we can have this. Okay, the eigenvalue that represent the variance of a particular principal component can actually be equal to 0. One of the eigenvalue can be 0. Okay, so but the only condition under which one of the variances can actually be 0, at least one or more can be 0, is when you are actually talking about, that's in a situation of high dimensional data. High dimensional data is when the number of observation is actually less than the numbers of features. But situation where that doesn't occur, situation where we have this, where the numbers of observation is greater or equal to numbers of p, then we expect any of the variance to be strictly greater than 0. That is exactly what it's trying to say. Because when it is strictly greater than 0, we're going to say, okay, that is linearly independent. Okay, linearly independent, the condition for linearly independent is that, how can I have linearly independent? Linearly independent is going to happen when I do not have high dimensional data. When the number of observations is greater or equal to the numbers of features, then I'm expecting all the eigenvalues to be greater than 0. We don't want them to be 0. And if it is not 0, then we're going to say that the corresponding data matrix S is actually going to be linearly independent. Okay, now I want to move right now. I'm moving to what we call the Cauchy-Squash inequality. The Cauchy-Squash inequality will give us a relationship that could lead to us getting correlation. I just want you to see that. The Cauchy-Squash inequality said when you square the covariance, when you see that, when you see S, let me write this so that you understand. You understand what I mean? If X represents, if this guy represents the covariance, element within the covariance is what we call SJK. Okay, which means covariance between a variable J and a variable K. Okay, now if this represents the covariance between variable J and K, now the squashing notice that when we square that, okay, when we square that, the result is going to be less or equal to the product of each variance. Okay, this was actually noted by Cauchy and Squash. Now, when I squared the covariance, you can try it out on any data. When you square the covariance, the result is going to be less or equal to the product of the respective variance. This is going to be the variance of variable J. This is the variance of variable K. When I multiply them, okay, then we're going to have this relationship. That's what Cauchy-Squash inequality actually talk about. And he said that this is only going to happen, okay, with the equality holding. That is going to hold if the two variables are linearly independent. Okay, the two variables that I'm actually focusing on, okay, Sj and Sk are linearly dependent. When I say linearly dependent, what does that mean? Like they are depending on each other. Situation where you got variables that are related. That's what it means. But when they are unrelated, we're actually going to say linearly independent. But do you know something? When we decide to find the square root of both sides, of course, when you find, when we find the square root of both sides, we already know that each of these has to be positive, right? The square root of positive, this is still going to be, each of this is still going to be positive. But if you take a look at this guy, it may be negative or positive. Don't forget its covariance. So what we're going to do is we're actually going to put an absolute value. Okay, the absolute value, we actually remove the negative. You get what I mean? So that's why we put the absolute value. So if we want to talk in terms of, what I'm going to say, this guy is a Cauchy-Squash when it comes to variances, and this is Cauchy-Squash when it comes to standard deviation. Does that make sense? Just wanted to see that. Now, I'm moving now. The next thing I'm actually going to walk you through, I've already shown you the covariance, matrix. How do we actually get this in out? Okay, so now if you want to get this in out, the hard way to do that is going by this. You start with defining your n. Okay, you define that. This is how to get the center matrix. You remember the other time I talked about center matrix, and of course divided by n minus 1. And here, if I'm focusing not on the entire data, okay, that's another way. There's another way to do that. This is the result I'm actually going to have. But another way to do that, okay, is through this. You know, whether using this approach or using this approach, I'm actually still going to call that an hard way to do that. But what is the easy way? Okay, now I needed to pay attention now. Oh my God. The moment I have the data matrix S, the easy way to find the covariance is that. Without any coding at all. Then when I have my data X, I'm just going to write COV into X, parenthesis X. That will give me my covariance. Is that not interesting compared to this programming, compared to this coding? That's a waste of time, coding. Okay, so that's why I said we have easy way to get it, we have hard way to get it. This is the easy way, the most easiest way to get the covariance. Okay, now you can check whether your results, you know, what you got, and the dimension. This is to confirm that the dimension of the covariance has to be the same. The numbers of rows and columns have to be the same. Okay, so what are we going to do next? What we're going to do next is correlation matrix. Okay, so what is the difference between the correlation and the covariance? Okay, you know, when you know, the covariance and correlation do the same things, but the covariance is not appropriate in some situation. Okay, and I'm going to tell you why. Okay, you know, both of them talk about how variables, how they varies together, or how they varies jointly. Okay, you know, situation where your variables have different scales or they have different units. Okay, now the covariance is not going to be a reasonable measure of variation. Okay, so imagine you were working with, maybe you're working on a unit, or maybe you're working on dollars. Okay, whether that's like a currency, and you now change that, you get a covariance for that, and you now change to another currency. Okay, and the same data, except that you're converting from one currency to the other, and you find the covariance. The covariance is not going to give the same results because of that. It's not consistent. Now, you know, you know, the measure that we can trust is a correlation, irrespective of the unit. Okay, because something is, we're actually going to do something to covariance to get a correlation. We're going to standardize the covariance. When we standardize covariance, okay, standardizing covariance will give us correlation, and that is why in multivariate analysis, you know, we normally make use of the covariance method. But I'm going to give more information in the next class, because the next class we're going to start from correlation matrix. Is there any question for me today before I go? Now, let me give you this information before I go. I've been recording my lectures, and